In question number 9, a bead of mass m is equal to 500 gram moves in a gravity-free region along the smooth fixed ring of radius r is equal to 4 meter. The bead is attached to a spring having natural length r and spring constant k is equal to 10 Newton per meter. The other end of the spring is connected to a fixed point O on this ring and AB is equal to 8r by 5. Line OB is the diameter of the ring. If normal reaction on bead due to ring at A is 0, then we have to check the validity of given options. So at this instant, if I calculate what is the extension in the spring, then this separation is given as 2r, that is the diameter. This separation is given as 8r by 5. Then I can calculate what is this length because this angle is 90 degree. So if I calculate this extension in this spring, then extension or elongation in the spring delta x can be written as 2r whole square plus 8r by 5 whole square minus natural length of spring r. So if I solve this, it comes out to be r by 5. It means that the spring force which is acting on this bead is k into r by 5, and suppose if I take this as my angle theta, then this angle is also theta, as this triangle OAC is an isosceles triangle. So the component of force in this direction is F into cos theta. So if I calculate the radial component of force, so the radial component of force is kr by 5 into cos theta. Now I have to calculate what is the value of this cos theta. So in triangle OAB, sin theta is equal to perpendicular, that is 8r by 5 divided by hypotenuse 2r. So it comes out to be 4 by 5. So the value of cos theta comes out to be 3 by 5. Now if I substitute this value cos theta, so it comes out to be 3kr by 25. Now in the question it is given that the normal reaction on bead due to ring at A is 0. So if V is the speed at this moment, then we can write m into V square by r is equal to radial component of spring force. That is equal to 3kr by 25. So if I solve this equation after substituting the data, the value of V comes out to be 6.2 meter per second. So option B is correct and A is wrong. Now the tangential force acting on the bead is Ft is equal to K into R by 5 into sin theta, and this must be equal to m into dV by dt. So the value of dV by dt comes out to be kr by 5 into m into sin theta. The value of sin theta is 4 by 5. So if I substitute the value of these physical quantities, then it comes out to be 12.8 meter per second square. So option C is correct and D is wrong. So the correct answer for question number 9 are option B and C. Let's move to question number 10. In question number 10, a point charge Q is placed just inside the corner of a cube of side length L on the body diagonal as shown. Then we have to check the validity of given options. If I consider the charge is kept at the center of a cube of side length 2L, then this is the extension of this cube whose side length is 2L. Then the total flux through this complete face is given by Q by 6 epsilon naught, and the flux through this face BC, G and F is given by 1 by 4 of this. Now for the original cube of side length L, face BCGF, face GF, face EFGH and the face CDGF, the flux, all these three faces are same. Similarly, the flux through the near faces are also same. So the total flux through the far faces is given by 3 times of Q by 24 epsilon naught. So it comes out to be Q divided by 8 epsilon naught. So option B is correct and A is wrong. In the cube of edge length A, the total flux all the near faces is phi1 and through all the far faces is phi2. That must be equal to Q by epsilon naught. This is the value of phi2. So the value of phi1 comes out to be 7Q by 8 epsilon naught. So option C is correct and D is wrong. So the correct answer for question number 10 are option B and C. Let's move to question number 11. In question number 11, Planck's constant h, speed of light c and gravitational constant g are used to form a unit of length and a unit of mass m. Then the correct options is R. We know that the dimensions of h is given by m1 L2 t minus 1. The dimension of c is given as L1 t minus 1 and the dimension of g is given as m minus 1 L3 t minus 2. In the given problem, L can be written as a function of s, c and g. So let h raised to the power x, c raised to the power y and g raised to the power z. So if I compare LHS and RSS, then the value of x comes out to be half, that is also equal to the value of z, and the value of y comes out to be minus 3 by 2. Similarly, if I solve for z, then m can be written as a function of h raised to the power p, c raised to the power q and g raised to the power r. So if I compare LHS and RHS and solve for PQR, then the value of p comes out to be half, the value of q comes out to be half, and the value of r comes out to be minus half. So I can see that option A, B, C and D are correct options. So the correct option for question number 11 are option A, B, C and D. Let's move to question number 12. In question number 12, a small quantity of solution containing Na24 radionuclide whose half-life is 15 hours of activity 1 microcurie is injected into the blood of a person. A sample of blood of volume 1 cm cube taken after 7 hours shows an activity of 294 disintegrations per minute. Given that radioactivity solution mixes uniformly in the blood of person and 1 curie is equal to 3.71 into 10 raised to the power 10 disintegrations per second, and the value of ln2 is to be taken as 0.7. So the initial activity A0 is given as 1 microcurie, so that is 1 into 10 to the power minus 6 into 1 curie is 3.71 into 10 raised to the power 10 disintegrations per second. So this is equal to 3.71 into 10 raised to the power 4 disintegrations per second. Now we know that at any time t, the activity minus dN by dt or the rate of disintegration is given by lambda into the number of active nuclei at that instant. In the question it is given that after 7.5 hours, the sample shows an activity of 294 disintegrations per minute. So at this instant, if I calculate what is the number of radionuclei present in the blood sample, then it can be written as 294 divided by 60, that is the disintegrations per second, is equal to lambda, that is ln2 divided by t half. So ln2 is 0.7 and the value of half life, that is t half, is given by 15 hours, so that is equal to 3600 second. So if I substitute the value of t half here, that is 15 into 3600, then n indicates the number of radioactive nuclei in the blood sample after 7.5 hours. So the value of n on solving comes out to be 3.78 into 10 raised to the power 5. So option B is correct and A is wrong. Let's check the validity of option C and D. In option C, it is asked the total volume of the blood in the body of a person is nearly 8 liters. So in order to calculate this, we know that the activity at t equal to 7.5 hour can be written as initial activity A0 divided by 2 raised to the power t divided by t half. So at this instant, the value of t is t half by 2. So we can say that it comes out to be A0 divided by root 2. So if I substitute this, the value of A0 is 3.71 into 10 raised to the power 4 divided by root 2. Now in the question it is given that 1 centimeter cube of blood sample contains an activity of 294 by 60 disintegrations per minute. So the total volume can be found out by 3.71 into 10 raised to the power 4 divided by root 2 divided by disintegrations per second in 1 centimeter cube. So that is 294 divided by 60. So this comes out to be 5.35 into 10 raised to the power 3 centimeter cube, or this can be further written as 5.35 liter. So option D is also correct. So the correct answer for question number 12 are option B and D. Let's move to question number 13. In question number 13, a parallel plate capacitor having capacitance 3 microfarad is charged with a battery of EMF E is equal to 3 volt, and then connection is removed as in figure A. After this, at t equal to 0, half of the distance between the plates of the capacitor is filled with a slab of dielectric constant K is equal to 3 as shown in figure B, and the system is allowed to attain steady state. Then we have to check the validity of given options. So in option A, it is asked the net heat dissipation in the circuit after t equal to 0 is 4.5 microjoule. So at t equal to 0, if I calculate what is the charge on the capacitor, then the charge on the capacitor is C into V. So the capacitance value is given as C, that is epsilon 0 A by D, and this is equal to 3 microfarad. So 3 microfarad into potential difference, that is 3 volt. So it comes out to be 9 microcoulomb. So the initial energy stored is equal to half into Q, that is 9, into V, that is 3. So this comes out to be 27 by 2 microjoule. Now in the second situation, when a dielectric slab is introduced, then the C equivalent is the capacitance of this capacitor becomes K into epsilon 0 A divided by D by 2. So it becomes 6C, and the capacitance of this segment becomes 2C. So the equivalent can be written as 6C into 2C divided by 8C. So on solving, it comes out to be 3 by 2 C, and the value of C is 3 microfarad. So it comes out to be 9 by 2 microfarad. So the final energy stored in the capacitor is half into Q square. So the value of Q is 9. So 9 into 9 divided by C final. So that is 9 by 2. So on solving, it comes out to be 9 microjoule. So the net heat dissipation delta H is equal to 27 by 2 minus 9. So it comes out to be 4.5 microjoule. So option A is correct. Now in option B, the modulus of charge appearing on the face of the dielectric. So the charge appearing on the face of dielectric Q dash is equal to Q into 1 minus 1 by K. So the value of K is 3. So this is 1 by 3. So 2 by 3 of Q, and the value of Q is 9 microcoulomb. So this comes out to be 6 microcoulomb. So option B is wrong. In option C, the net potential difference between the plate is 2 volt. So the net potential difference, suppose this plate is at A and this plate is at B, then the potential difference VA minus VB can be written as, if the initial electric field is E in this region, then it can be written as E by K into D by 2 plus E into D by 2. So this can be further written as E into D by 2 into 1 by K plus 1. So the value of K is 3. So 1 by 3 plus 1 is 4 by 3. So it is equal to 2 by 3 of E into D, and the initial potential difference is 3 volt. So this comes out to be 2 volt. So option C is correct. And in option D, the net force on the negatively charged plate will not change. So this option is also correct. In option D, the net force on the negatively charged plate will not change. Since the force due to the charges appearing on the dielectric on the negative plate is 0, so the net force on the negative charged plate will not change. So option D is also correct. So the correct answer for question number 13 are option A, C and D. Let's move to question number 14. In question number 14, a satellite of mass m is revolving in a circular orbit around the Earth at a height r above the Earth's surface. Mass of Earth is m and its radius is r. At some point of time during the motion, the satellite is given an additional kinetic energy of gmm by 8r such that its speed increases. Then we have to check the validity of given options. Let's analyze the situation. Suppose this is the Earth of radius r and the satellite is at a distance r from the surface of the Earth and it is given some additional kinetic energy. So by applying the principle of conservation of mechanical energy, we can write the energy of the satellite at this instant is potential energy by 2, so minus G into M into capital M divided by 4R. Now the additional kinetic energy provided is G into capital M into small m divided by 8R, and that must be equal to, suppose it will move in an elliptical path, then the total energy in the elliptical path is given by minus G capital M small m by 2a, where 2a is the length of the major axis. So if I solve this equation, the value of a comes out to be 4r. So semi-major axis of elliptical orbit is 4r, so option B is correct. Now, when the satellite reaches to this position, we have to find out what is its speed. So this is 2r, then this will become 6r. So the total energy at this instant is minus gmm by 8r after providing additional kinetic energy. So this is equal to the kinetic energy at this instant, that is half m into v square minus the potential energy of the satellite is given by G capital M into small m by 6r. So on solving, the value of v comes out to be under root of G capital M by 12r. So option C is correct. So the correct answer for question number 14 are option B and C. Let's move to question number 15. In question number 15, an ideal monatomic gas undergoes a process in which its internal energy relates to the volume as U is equal to alpha into under root V, where alpha is a constant. Then we have to check the validity of given options. So U is the internal energy, which can be written as N into Cv, that is constant, into T, that is equal to alpha into under root V. So we can say that T is proportional to under root V. From the ideal gas equation, we know that PV is proportional to T and it is proportional to under root V. Or if I square this, I can say that P square into V square is proportional to V, or P into V raised to the power half is equal to constant. So if I compare with the polytropic process, PV की power x is equal to constant, then the value of x comes out to be half. Now, the molar heat capacity of this polytropic process can be written as C is equal to Cv plus R divided by 1 minus x. So the value of Cv is 3R by 2, and if I substitute the value of x is equal to half, then it comes out to be 2R. On solving this, it comes out to be 7R by 2. So option D is correct and B is wrong. Now, from the first law of thermodynamics, we can say that the value of delta U from this equation can be written as N into 3R by 2 into delta T, and the work done by the gas delta W can be written as N into 2R into delta T. So if I take the ratio delta W by delta U, then it comes out to be 4 by 3, or delta W is equal to 4 by 3 of delta U. Now in the given options, if the internal energy increases by 90 joule, then I have to substitute the value 4 by 3 of 90, then it comes out to be 120 joule. Then the work done by the gas is 120 joule. So option C is correct and A is wrong. So the correct answer for question number 15 are option C and D. Let's move to question number 16. In question number 16, consider the situation shown in figure given below. The force F is equal to mg by 2. Area of cross section of the string is A, length is L, and Young's modulus is Y. Neglect the friction. So if I draw the free body diagram, then mg is acting in this direction. So the acceleration of the system can be written as mg minus mg by 2 divided by 2m. So it comes out to be g by 4. So if I write the equation on the block of mass m, then tension is acting in this direction. So T minus mg by 2 is equal to mass into acceleration in this direction. So that is g by 4. So the value of T from here comes out to be 3 by 4 of mg. So the stress can be calculated as T by A. So it comes out to be 3 by 4 mg by A. So option B is correct. Now we know that Young's modulus is equal to stress by strain. So the value of strain is 3 by 4 mg by AY. So option A is wrong. Now we have to find out what is the potential energy developed in this string. So the potential energy developed in this string is equal to half into stress into strain. So that can be written as stress square divided by Y, Young's modulus, into volume. That is A into L. So if I substitute the value of stress here, then it comes out to be 9 by 32 m square g square L divided by AY. So option C is correct. So the correct answer for question number 16 are option B and C. Let's move to the first paragraph containing question number 17 and 18.